I was fortunate and privileged to have Yakir as my teacher during my student years in Tel Aviv University. Beyond the many things that I learned from Yakir, I took two lessons for life. One came at a course Yakir gave, which was called Student Seminar. So each student had to give a seminar on a topic of his or her choice. And Yakir insisted that the topic and the subject should be creative and original. So I approached Yakir with the idea of talking about the non-associativity of certain arithmetic operations and the relation to non-determinism of quantum mechanics. I'm not sure whether you remember it. I remember the title. I have no clue what I said. Probably it was contentless. But I remember Yakir's response. He was very encouraging. He said, yes, this is a very original title. So I carried it with me for life, putting originality and creativity very high on my agenda. The second was following a course on advanced electromagnetism that Yakir gave. So he was standing in front of the class, and as he was talking, he would go pace from right to left, left to right, and the faster he wrote integrals on the blackboard, the faster was the pace. So we needed to listen, to absorb, and then make some physical exercise with our heads. And the lesson was that physics exercises and physical exercises come hand in hand. And till this very day, when I have a difficult problem, I find myself in my office pacing back and forth, trying to solve the problem. These are the two lessons. And then fast forward many years. The year is 2007. I participate in a conference at the ICTP in Trieste, and Yakir is giving a talk on weak values and related paradoxes. And to my shame, I had never heard about weak values till that day. So I attend Yakir's talk. I find it exciting, but I understood nothing. So I decided to spend a day trying to absorb and figure out what Yakir was saying. And this day goes 16 years later when I am absorbed with the physics of weak measurement. So thank you, Yakir, very much for steering me in these very exciting directions. And the subject of this talk will indeed be steering, quantum steering. This is a partial list of my main collaborators over these 16 years on different topics. And in particular, I'm proud to have been collaborating with several experimental groups trying to implement these ideas on different platforms, going from superconducting qubits to optics to called ions. So this is the first title of my talk. The second title of my talk is something much more specific, steering the unsteerable and the appearance of weak values in this context. And I will expand, of course, as I go and follow this topic. This is a very recent work done in collaboration with Samuel Morales, Alex Zulov, and Reinhold Egger from Düsseldorf, Igor Gorny from Karlsruhe, I mean, it's a great team. So what is steering? Steering is a very old notion in quantum mechanics. And this is a text written about the correspondence early on in the game between Schrödinger and Einstein. So it says the EPR argument led to long-lasting discussions, but already directly after the publication of the EPR, Schrödinger noted that a very interesting phenomenon in the argument. The first party can, by choosing the measurement, steer the state on the other side into an eigenstate of position or momentum. This cannot be used to transmit information, but still Schrödinger considered it to be magic. So this observation was later developed and studied by various authors, including Weissman. But the point there was that steering did not imply what the other party, I do something to a particle A, it doesn't determine uniquely what a particle B will be. Therefore, I cannot transmit information. The steering I'm going to talk about today, takes this notion one step forward. I'm going to use quantum steering in order to influence the quantum state of a system in a deterministic and hopefully very useful way. So before doing so, let me remind you a very fundamental insight about the difference between classical measurement and quantum measurement. So in classical measurement, we may or may not have back action on the measured system. I'm standing at the side of a highway recording the speed of a passing car, and the driver of this car will have no idea that she has been measured until she gets a ticket for speeding at home. But classical measurement may also result in a back action. My friend comes to me and tells me, Yuval, I suspect that I have some problem with my car. Can you make a measurement and tell me whether there is a gas leakage from the car or not? And I say, of course I can. I approach the car, take my matchbox, I light the match, and if the car explodes, I know that there was a problem. By contrast, quantum measurement must result in a back action, which seems at first sight to be something bad, something unwanted. But the question is whether we can harness this back action in order to nudge the system, to steer the state of the system towards a desired target state. So this has to do with the quantum state engineering. But before I'm talking about quantum steering and quantum state engineering, the question is why I need it at all. Because there are other ways to lead the system to a desired state. For example, by projection. I have a spin half pointing at this direction. I want the spin to end up pointing in the direction of the direction up, direction of the North Pole. And I can just project it onto the direction of SZ. But by doing so, I have indeed a probability P to end up with up, but also a probability of -1 minus P to end up down. So success in this case is probabilistic, and we don't want a probabilistic success. We want success. By the way, there is a set of beautiful measurements by Siddiqui and his group who used not projective measurements, but set of weak measurements of spin half, always measured in the direction of SZ. You can see different trajectories here of this spin half, starting with the spin directed in the SX direction. The projection in the Z direction, the initial projection in the Z direction is 0. So you can see the stochasticity of these trajectories. Some of them end up in the North Pole, some end up in the South Pole. So indeed, success is probabilistic. There are other methods to get a desired state of the system. For example, suppose we want to end up in a state which is a ground state of the system's Hamiltonian. What we can do, we can very weakly attach the system to a heat bath and cool down the heat bath, take the heat bath at a very low temperature. The idea is that by heat exchange, the system will be eventually driven towards the ground state. The problem here is that if the system becomes large and complicated, the time it takes to cool the system and the temperature it takes the reservoir needs to be cooled to becomes impractically low. So this is becoming very impractical for a large system. In addition, for certain complex systems, we can get stuck in some metastable state, and we will not be able to cool it further. And lastly, we can take a system in a given state and apply a Hamiltonian and bring it to our desired quantum state. For example, with the spin half, suppose the spin half is pointing in this direction, we want to bring it to the SZ up direction. We can apply a perpendicular magnetic field, which will rotate the spin and then stop when the spin arrived at the North Pole. But the problem with this is that we need a precise knowledge of our initial state and precise control of the time and the strength of the magnetic field we apply. If we make an error, then we don't end up in the desired state. So our wish list is quite greedy. We want to steer towards a desired target state. We want to start with an arbitrary, unknown to us, initial state. We want the steering to be robust against a certain perturbation that may happen in the course of our protocol. We don't want a precise control on the time of the operation. And we would like to be able to steer towards a target state which is not necessarily a ground state of a known Hamiltonian. So here are the principles of a steering protocol. We prepare a detector, which is a simple degree of freedom, in a designated state. For example, if the detector is a spin half, we assume that we can prepare it in the spin half. The system is complex, but the detector is simple. So we assume that this simple degree of freedom can be prepared in the spin up direction. Then we couple the system detector through a system detector Hamiltonian and let them evolve. We decouple them after the evolution time delta t. And the question is then what we do with the...
Bill has a question.
Yes.
I'm just wondering, isn't prepared detector in a designated state just the problem that you're trying to solve?
Okay, very good question. So keep in mind that I have a detector which I can prepare in the designated states by any of the methods that I put before. For example, cooling down the detector. The detector is simple, single degree of freedom, spin half. The system can be extremely complex, can contain many degrees of freedom. So that would be a challenge. Okay. So So the question is what I do with the system detector after I decouple them. And one possibility is that after letting them evolve for some time, I throw away my detector, and I repeat this with a new detector, a newly prepared detector. So in mathematical terms, I trace out over the detector readout, and I call this a blind measurement. I don't look at the detector. It's an example of passive measurement. So then I prepare the detector afresh and repeat the operation. So let me demonstrate how this works with a trivial thing. And you're absolutely right that this trivial example doesn't make any sense except for pedagogical reasons, but immediately I will show how it works for a more complicated system. So the trivial thing will be that the system is spin half and the detector is spin half. Let me first refer you to some of the works that have been done in recent years in this direction. I have a system which is spin half, which I would like to steer towards SZ up. The system initially is in an arbitrary state. The detector is always at each measurement step prepared in the up direction. And I have a system detector Hamiltonian, which defines my evolution operator on the universe. The universe is the product of the system space and the detector space. And specifically for this problem, I choose this system detector Hamiltonian, which can be written in terms of raising and lowering operators in the space of the detector spin and the system spin. So now comes the first very important ingredient in this steering protocol. Directionality. The detector is prepared in the state up. And before the measurement, the state of the universe is the running state of the system times the state of the detector, which is up. So now, when I apply this system detector Hamiltonian on the state of the universe, clearly, this operator will give me 0 because the detector spin is up. So applying S detector plus on that will give me 0. So this is inactive. So although the system detector Hamiltonian is Hermitian, I get rid of that, which gives me directionality, which is why at the end of the day, I'm able to steer towards a particular desired direction. Mathematically, what I do in this stupid blind steering is I take the product state, which is the running density matrix of the system, times this is a projection onto the detector in the direction up. Let this density matrix of the universe evolve with the system detector a unitary evolution, and then trace over the degrees of freedom of the detector to obtain the new n+1 step reduced density matrix of the system, the new state of the system. So here is how it works in practice. I parameterize the state of the system with a 2x2 matrix, which comprises the unit matrix plus a linear combination of Pauli matrices. This S is a coefficient, is a 3-vector of coefficients, coefficient times sigma x, coefficient times sigma y, coefficient times sigma z. This is an example where I start with the pure state. This is my initial state, and you can see that after about 150 steps, the only component that is left is the sigma z +1. I managed to steer the system towards my desired state. This is an initial state, which is a mixed initial state. And again, after 120, 130 steps, I managed to steer the system in the desired direction. But as you correctly said, this is a triviality. And let me only mention that all these operations, those of you who are experts in Lindbladian dynamics, this is closely related to Lindbladian dynamics for reasons that I don't have time to discuss. But I can now go to a many-body complex system with many degrees of freedom. So there I need to use many detectors. And there are three principles I need to adhere to. One is that each detector measures something local. Here in this example, 2 spins. Second, the complexity of the system detector Hamiltonian should not increase with increasing the size of the system. And similarly, the number of detectors should be extensive, should not grow faster than the number of degrees of freedom of the system. So an example is a strongly correlated many-body model known as the AKLT, or Affleck-Kennedy-Lieb-Tasaki, which is a chain of spin 1 components. One can write the Hamiltonian, which I have not written, but the ground state of that Hamiltonian of a spin 1 chain consists of a state where every 2 neighboring spins, every 2 neighboring spin 1 states, every link has a component on total spin 0, a component on total spin 1, but no component on the total spin equals 2. This applies to this link, and to this link, and to this link, and so on. So I can design a Hamiltonian, I can design a protocol like that, and I can let the system, the initial state run, and I measure the distance of my running state from the target ground state of the AKLT model, and you can see that convergence is very fast, is exponential success. So that's what I wanted to say about stupid passive steering. I can say much more, but I would like to switch now to a more sophisticated steering, which is active or decision-making steering. And what is the difference?
Can I ask a quick question before you go on? You said at the beginning that one way of controlling a system is, of course, to put it in contact with a cold reservoir, but that's inefficient. I just want to understand if there's really a difference between the passive steering and that. It seems to me here you're just using a conservation law. Isn't it the same as just resetting a reservoir to T equals 0 and letting it couple by exchange of energy?
Yeah. The point is this. I don't let the detector, the local detector, and the local degrees of freedom, I don't let them equilibrate, which would be when I tried just to cool the system. I really apply an active Hamiltonian, dynamic Hamiltonian, which does something. Had I done what you suggest, then if the system becomes very large, the gap between the ground state and the next state can be exponentially small, and I will never be able to achieve a particular state. Thank you for the question. So this was the principle of my stupid blind measurement. This is the running state of the system times the detector prepared in its, let's say, spin-up state. I apply some unitary operator. I perform measurement. Let's say that my detector can show 0 or 1. By performing the measurement, I have back action on the system. And then I reset the detector or throw away the detector and start with a new detector and start it all over again. This is what I just described to you. When I go to active steering, there are 2 new elements, 2 new ingredients here. The first one is that I don't just throw away or trace out the detector. I actually look at the readout of the detector, and I note it, put it in my notebook. So I end up with a series of vector of the read out history, 100, 10, 10, etc. This is the ingredient number one. The second ingredient is that I would like to take this history and, using this history, I would like to decide which evolution operator I should use for the next step. These are the two new ingredients. And I would like to choose a unitary operator for the next step in order to improve the protocol. Improving the protocol makes it faster, makes the fidelity, the convergence towards my desired state better. So there are two elements that I need here. First of all, I need to have a set of system detector Hamiltonian or system detector unitary evolutions. I denote members of this state by alpha, and they relate to each other non-trivially. They should not commute. So there is this set. The second element is that I need a policy. I need a policy, given the history, to decide which of these operators I should take for my next step. So we came up with two paradigmatic ways to decide on a policy, two different policies, and I would like to describe one of them. And I call this policy a cost function policy or quantum compass. So we introduce a cost function. So this cost function is to be minimized in the protocol. For example, this is the overlap between the running density matrix, the running state of the system, and the target state. If we reach the target state, this is 1, so we have 1 minus 1, this is 0. Otherwise, this is a positive valued function. So we want to reduce this cost function in the most efficient way. And what we actually want to do is to choose a set of unitary evolutions, a set of system detector Hamiltonians, H alpha 1, H alpha 2, H alpha 3, and so on, that brings the system to the global minimum of the cost function in the fastest expected time. But this is impractical, because in order to know what is my best trajectory, I need to have a global view of space and time, and this is too costly. So I replace this by a more modest, greedy version. I would like to make sure that the next step will be the steepest descent, will give me the fastest decrease in the cost function. So here is after some analytic results, we need to eventually run this through a computer. And this is an example of this AKLT model with 5 spins. We have also results for 6 and 7 spins. So if we use a stupid blind steering protocol, this is the histogram of the runtime, the number of steps needed in order to get to a state with fidelity 99%, whose overlap with the target state is 0.99 or better. If we use the active measurement step, this is the histogram, not different in scale. So it's an order of magnitude better. If we go to 6 and 7, it's even better than the order of magnitude. We really improve the yes, right. So this is much faster. This is much faster. Yeah. So I put them one on top of the other. This is the histogram for the active. This is for the passive. You can see the difference, and the difference improves as my system becomes larger. So
what you do in this feedback is you measure the state you have, overlap it with the state you want. Is what you do?
No, okay, no. What I do is the following. I have a running step, and I have several possible unitary operators. So if I apply unitary operator, I don't know what will, and I then couple to the detector, I decouple to the detector, I look at the readout of the detector. I don't know what is the result I will obtain because this is stochastic. But what I'm saying is that if I use a particular unitary operator, I average over all possible outcomes of my detector, and I calculate what on the average will be the improvement in the cost function. I do it for unitary operator number 1. I do it for number 2, number 3, and I choose the best which on the average will give me the best decrease in the cost function.
So you don't make any measurements along the way?
Each time I make a measurement, the unitary operator is that I couple the detector to the system, I decouple, I look at the detector.
And for the AKLT, what's the detector? Is a single spin?
The detector is a single spin half coupled to two spin ones. I can write the Hamiltonian, but I don't want to go into details.
No, it's fine.
But it's a three spin Hamiltonian, detector and 2 spins of the system. But I'm trying to avoid the, yeah, okay. So before I proceed, there is a big warning here, big warning. Let's take an example. Suppose I have a simple target state, which is 0, 0, 0, 0, and my initial state is 1, 1, 1. And I have some clever steering that takes me from 1, 1, 1 to 1, 0, 0, 1, 1 to 1, 0, 0, 1, 0, 1, 0, and so on. You can look at that, and it's clear that I'm getting closer and closer to my target state. Yeah. But in each intermediate step, the overlap between this or this or this with the target state is still 0. So in terms of overlap of intermediate step with my target state, I do not improve anything. The landscape of my cost function is completely flat. So the cost function will not tell me anything about making it closer and closer. And this is those of you who come from condensed matter know about Anderson orthogonal catastrophe. This is the first cousin of Anderson orthogonal catastrophe. So in order to overcome that, I need to replace the global cost function with the local cost function. I take my running state and I trace out many degrees of freedom except a segment, so I get a reduced density matrix of my running state. I get a reduced density matrix of my target state, and I look at the overlap between those local reduced density matrix, and by doing so, I will be able to see improvement in the cost function. So I need to use the local cost functions. So
you have this orthogonality, but sometimes it's more orthogonal when it's many ones and many zeros.
So this is exactly the case. So this is why if I look at segments, I trace out everything. I look at segments, it will tell me that I'm getting closer. This is why I need to do something local. Exactly. But globally, I will not be able to see anything. Okay. That was a quantum compass, a cost function paradigm. There is another paradigm, which is quantum state machine. I will not discuss it here today. So now I'm coming to the last chapter of this saga till now. But before that, I want to make a pause and devote one slide to frustrated versus non-frustrated models. So imagine I have a system with many degrees of freedom, and I write the Hamiltonian as a sum of local Hamiltonians. So each HI operates non-trivially and locally on the system. So frustration-free problem will mean that if I take the ground state, or the ground state manifold, it is simultaneously, of the entire system, it is simultaneously the ground state of each HI separately, individually. This, by the way, does not mean that the HIs should commute. They can be non-commuting. But they should share the same ground state if I want to call this non-frustrated model. If this is not the case, this is a frustrated model. So there is a theorem, very interesting theorem, by Ticozzi and Viola, saying that if I use a stupid, passive, blind steering, I can steer only non-frustrated Hamiltonians. So there is a no-go theorem. I cannot use passive steering to get to a state which is frustrated. What I've shown you so far is that with active steering, I can improve my performance. I can improve my performance by a lot. But now the question is whether I can use active steering not only to improve what passive steering can do, but to do something which passive steering cannot do, whether I can overcome this no-go theorem. And the answer, as you may expect, otherwise I would not be standing here, is yes. And I'm going to give here 2 examples of states which are frustrated states. One is called the Greenhorn-Zeilinger. This is a superposition of 0, 0, 0, 0 plus 1, 1, 1, 1, 1. The other is called W state, which is 1, 0, 0, 0 plus 0, 1, 0, 0, 0 plus 0, 0, 0, 0, 1. Both states can be shown to be frustrated, and they are not steerable with stupid passive steering. So in order to do that, I want to combine, to take active steering and combine 2 ingredients here. The first ingredient is that I still stick with the local steering, and local will be really local. I'll show you momentarily. The other ingredient will be entanglement swapping, and I'll explain each word in this title. So first of all, local steering. So suppose I have a long chain of qubits, and these are 2 qubits, the qubit number n plus 1. Qubit is like spin half. And these are my detectors. This detector will be coupled only to this qubit. This detector will be coupled only to this qubit. So it's really a local measurement. Each detector measures only 1 qubit. So I implement a certain Hamiltonian. I will write down the Hamiltonian momentarily. And as a result, after switching off this Hamiltonian, I generated entanglement between this detector and this qubit, and between this detector and this qubit. Now, when the Hamiltonian coupling the detectors and the qubits is switched off, I'm going to do the following. I'm going to go to the subspace of detectors and project these 2 detectors onto a basis of Bell states, which are entangled states. So I'm going to project this guy onto entangled states. But now I recall that there is a theorem of monogamy in quantum mechanics. If A is entangled with B, and now I try to entangle A with C, I'm going to undermine the entanglement of A and B, the original entanglement of A and B. So if I force these 2 guys to be entangled, I'm going to undermine the entanglement of each detector to its qubit friend. But I'm going, in doing so, in performing this measurement, I'm going to apply entanglement between n and n plus 1. So this is the idea. So if I'm now in a running state, I already had the entanglement, and I continue, this entanglement will only increase. And if I do it for the pair of qubits n and n plus 1, and then n1 plus n2, and so on, I can give rise to entanglement propagation in my system. So let's see how each step goes. Here is my Hamiltonian connecting a detector. Detectors degree of freedom are denoted by tau. These are Pauli matrices. And this is the Pauli matrix of a detector number n. The beta is x, y, or z. Similarly, sigma is the Pauli matrix of the qubit, of the system's qubit. J is the amount of coupling. So by turning on and then off a unitary evolution with this Hamiltonian, I generate a system detector entanglement. And if J is small, I will introduce weak entanglement. If this is J is large, I will generate strong entanglement between these two guys. Next, I'm going to project these two guys onto a basis of Bell states. So I have Bell states with even parity, odd parity, and then in each parity I can have a symmetric and anti-symmetric combination. All in all, I have 4 Bell states. So this is the protocol, and it relies heavily, as I said, on quantum monogamy. And now what I need to do, I have a whole a family of possible Hamiltonians, detector system Hamiltonian, which I can use. So in each step, I should use the Hamiltonian, which gives me the best improvement of my cost function. So this is this slide is going to be a bit mathematical. This is the change in the cost function, which will be the overlap between the running density matrix and the final states. And I can write this change in the cost function in terms of these guys. It turns out that this change in the cost function includes the weak value, the relevant weak value of this segment of these 2 qubits. And remember, each time I take the Hamiltonian, which is the best suited for reducing the cost function. And now I have, with the appearance of a weak value, I have good news and bad news. The good news is that if the running state psi and the final state psi final are very far from each other, are nearly orthogonal, this weak value is going to be huge, and the improvement in my cost function is going to be very significant. I will have something like weak value amplification, which we encountered in many other instances. The bad news is that if the target state is the approach, or nearly approach, the running state is just a phase times the final state, then one can show that the weak value is real, and the right-hand side will be positive, which means that I cannot have any improvement in my cost function. I'm stuck. So there are two reasons or two scenarios for being stuck. One is that this is my Hilbert space, this is target state, but I have a manifold of trap states where my cost function cannot improve any further. The other scenario where this may happen is this exactly Anderson orthogonal catastrophe, which I demonstrated to you before. So in order to get over that, I will need to develop a cost function which is not global, but also includes local components. So I have a weighted sum of cost function which is global, which includes all spins, and local, which includes only part of the spins. And with this, I'm able to steer towards unsteerable states. So this is the histogram of the number of steps needed for the GHZ state and for the W state. These are the number of states needed to obtain fidelity of 97%. And you can see that indeed, this is doable. It is doable.
Yuval?
Yeah.
Excuse me, a question. I don't understand. The frustration is not a property of the state, it's the property of the Hamiltonian. Frustrated or not frustrated depends on the system, of the Hamiltonian system. And you're talking about frustration or non-frustration, the level of states.
Yeah. No. So you're right. Thank you for that. I was a bit loose in using frustration. What I mean is that with the GHZ and W, I can invent Hamiltonians for which the GHZ will be a ground state. I don't know how to invent Hamiltonians which will be non-frustrated for this. Thanks. So
Sorry, if you just have minus some large factor times the projector onto the GHZ state.
It should be a local.
You want it to be a local?
local, yes. Global, I can do whatever. I mean, I can always invent something that scales up with, n degrees of freedom, n plus 1 degrees of freedom. Yeah. I mean, the locality is a holy cow here. This is the story with frustrated models which are unsteerable with passive blind protocols and are unsteerable with Lindblom dynamics, which many people do. This will not work here. We need something more sophisticated. So I'm coming to a summary of my talk. What I told you, the story I told you, concerned the repeated weak measurements, harnessing the back action into steering the system to a desired target state. I first discussed the blind or passive measurement, then active decision-making steering, which is applied to states which are steerable, but now I can make it faster and higher fidelity. And I mentioned two paradigmatic approaches, quantum compact and quantum state machine. And then I showed you that with active decision-making steering, combined with entanglement swapping within the detector subspace, I can steer towards states which are ground states of frustrated Hamiltonian states that are not steerable. And with this, I would like to conclude many more groundbreaking ideas, Yakir. Thank you.
Great. What are the practical uses of this?
What?
What are the practical uses of steering?
Okay, so the practical uses. Okay, so I can see two directions. One direction is a bit more fundamental physics. I'm abandoning the notion of Hamiltonians, I'm considering states, and I would like to, I can generate and access complicated many-body states and explore quantum phase transitions, correlations, and so on, states that I usually or may not be accessible just by doing Hamiltonian physics. The practical, the more practical or applied directions are again two. One is that I can use this not only to prepare states, but also to manipulate states. So I can use this to generate logical gates, which are good tools in quantum information. The other has to do with the field of quantum annealing. I can use these local detections to optimize the way I'm cooling a system. But that's another talk.
Thank you. Here, Adi.
Yeah, I mean, you are the chair.
Yeah, go ahead.
So you explained that you cannot steer frustrated Hamiltonian by passive steering. Is the converse true also, that if an Hamiltonian is frustration free, then it can always be steered by passive steering?
Okay. Are you asking me as a mathematician or as a physicist? I'm not a mathematician. Okay. I don't know a theorem that says so, but frankly, any model that we tried and was non-frustrated turned out to be steerable, and I can sort of understand because I need to do. I mean, non-frustrated has to do with local Hamiltonians that can be minimized, and I can access this locality by coupling. But how to prove a mathematical theorem, I don't know.
So again, maybe a physical insight about a computational problem or mathematical problem. It's hard to quantify the computational complexity of finding the ground state of commuting local Hamiltonians and non-commuting local Hamiltonians. Can you say something about the complexity you find in steering towards those states of commuting versus non-commuting local Hamiltonians?
No, okay. Let me say. When I'm talking about a non-frustrated, I'm not talking necessarily about commuting Hamiltonians. If my local Hamiltonians are commuting, the problem becomes trivial. It just decouples into local problems which I deal with.
The ground state of such.
The fact that the ground state is the same does not mean that the HI are commuting. They only share the ground state.
Right.
So the non-trivial examples are the AKLT, are where the local Hamiltonians are non-commuting. Nevertheless, they are frustration-free. Now, you want, I'm not sure, there are certain criteria of complexity, and actually I have now a PhD student who is devoted to exploring that, but at this time I cannot say anything intelligent about quantifying the complexity.